Okay, hi everyone. Welcome to the Ethereum sequencing and Preconfs call number 2. This is our third call. The previous calls focused on the basics of the design of Ethereum sequencing with preconfirmations, and we also did a round of intros to kind of gauge interest in base sequencing in general. And the focus of today's call is on potential downsides, potential risks and concerns that people have with base sequencing. And we have 7 presenters who will each focus on one separate risk or concern. We're going to try and keep it quick because we don't have that much time. The goal really here is to try and understand the concern, not so much to solve the concern. So if you have any questions, please keep them around like clarification of what the concern is as opposed to trying to solve it. The first presenter is Ellie Davidson from Espresso. Ellie, the floor is yours.
Okay, yeah, perfect. Let me just quick share my screen. Okay, so there should be some slides up now. So today what I want to talk about is this fundamental trade-off we have between L1, L2 interoperability and L2 preconfirmation finality. So by L1, L2 interoperability, I mean like we want to be able to do atomic swaps between the L1 and the L2. We want to be able to react to L1 state very quickly on the L2. And then by preconfirmation finality, I mean, as a user, how confident am I that my preconfirmation is going to actually mean that my transaction becomes final on Ethereum? And so we kind of have this spectrum and this trade-off where on one end we have slow interop, but we get really strong preconf guarantees. And on the other end, we get weaker preconf guarantees, but really good interop with the L1. So the first open question that I want to bring is what exactly are preconfs promising? Are they promising L1 finality or L1 inclusion? So I think that they should promise L1 finality because this is what the user cares about. And this is actually what L2s today are essentially promising is L1 finality. But I think that we should be mindful about what we're actually promising. So from there, I just want to introduce this idea of conditional finality, which I think has been brought up in previous meetings, but it's this finality that an L2 block is only going to become finalized if a particular L1 block becomes finalized. And I think that this is a useful way to look at any L2. So any L2 has conditional finality, even non-based L2s. But the difference is that non-based L2s can choose a already finalized Ethereum block or some Ethereum blocks that's like sufficiently deep in the chain that it has a very low risk of being reorged. So this is kind of represented by these like basketballs on this spectrum. A non-based sequencer or non-based L2 can choose anywhere on the spectrum, but most of them tend to choose towards the left side. But the issue is that with based sequencing, we kind of are forcing rollups to be on this right side because the L2 data is being proposed in the L1 block. They naturally have to be conditioned on the preconfers block and not on some future or some previous block. And this means that there is a higher chance of reorging. So as a quick caveat to this, you can say, well, in base sequencing, sure, it's my user preconfirmation is conditioned on the preconfers block, but what about includers? Includers could include the transaction in their block before the preconfers block. And to this, I say, yeah, that is true. Includers could do this, but I think it's important that we understand that includers are not actually part of the pre-confirmation promise. We can incentivize includers to include transactions earlier than prior to the preconfers block, but we can't force them, and it's not part of the promise. So I think that this is something we can like optimistically hope for, but we can't guarantee. And so with that, I want to say, well, then, like, what is the risk that I'm talking about to base sequencing? And specifically, the risk is that because of this conditional finality and because of the fact that based sequencers, as we've been discussing them today, because they are forced to have weaker pre-conf finality, they have a worse experience than current L2s, and they actually, in a way, have a worse experience than the current L1. So current L2s, like I said, a lot of them are conditionally final on a finalized Ethereum block or some very deep Ethereum block that's almost never going to reorg. And so because of this, as a user, once I get a pre-confirmation from a centralized sequencer or a decentralized sequencer, I can be pretty much 100% sure that my transaction will become final. So this is a very big deviation from the current state. And it's also worse than the L1 state because, like I said, in the L1 state, if I submit my transaction to the public Ethereum mempool and it shows up in the current block, then, okay, I need to wait like 30 seconds, 60 seconds to see that it's sufficiently deep in the Ethereum chain. But with base sequencing, it's not on the current block, it's on the preconfers block. And so the preconfer might not, be the proposer for like 5 or 10 blocks. So I can't actually start waiting for to see if my pre-confirmation is going to become final until the preconfer actually proposes their block. Maybe an includer includes my transaction before that, but there's no guarantee that that happens. So I wanted to keep this super quick so we can discuss. But basically here's kind of what I would say the takeaways and the open questions are. So one, I would say currently based rollups are forced to have weaker pre-conf finality. It's great that they get really good L1, L2 interoperability, but this might actually not matter to all users. And a lot of users are really going to value this like strong finality that L2s offer today. Second takeaway is I think that we should be very explicit about what we're promising with a pre-confirmation. And I think what matters to a user is L1 finality and not L1 inclusion. And then finally, includers are not part of the pre-confirmation. So I think that they're very valuable to helping the base sequencing experience, but we need to be mindful about the incentives so that they're properly incentivized to actually include pre-confirmed transactions. And we also need to be mindful that they are not part of the pre-confirmation promise. And so we cannot rely on that as a guarantee that they will include transactions. So, and then really quickly, I just wanted to go over some possible solutions and some thoughts. So one is execution tickets. You could say, well, with execution tickets, we should have fewer missed blocks, maybe fewer reorgs because we're going to have less timing games, et cetera. And so maybe if the chance of reorging is a lot less, then maybe we're less worried about this. Maybe instead of having to wait for like 5 Ethereum blocks deep, I as a user feel comfortable waiting for like 1 block or something like that. Another option is insurance or slashing for reorgs. So this is based on the idea that a pre-confirmation should be promising L1 finality. So even if the preconfer is promised, we could optionally slash them if their block gets reorged and return this to a user in the form of insurance. So this is, this is definitely helps the user experience. They get, rewarded if their transaction does not become final, but obviously in this case, we would be slashing preconfers for something that is not their fault. And then finally, I just want to mention a quick solution that Espresso has been working on. And this is, well, perhaps we can actually allow more customizable conditional finality. So perhaps we can say, like based rollups or non-based rollups today that can choose to be anywhere on the spectrum between, strong finality and weak finality, we can say based rollups can choose that as well. And we could even go a step further and say, why don't we let users choose that on an individual transaction level? So that's also something that we've been working on in Espresso. But I'll end there, open it up for discussion. But yeah, the key takeaways is that you have this fundamental trade-off between finality and L1, L2 interoperability, and base rollups do not currently have a lot of flexibility to choose that trade-off.
Perfect. Thank you, Ellie. We have a couple minutes. George, you have your hand up.
Hey, thank you, Ellie. I think what you are plugging here as a risk is absolutely wonderful, and you're absolutely spot on. And I agree with you that having the gaps between preconfirmers actually is something that's going to cause probably worsening of the user experience. And I don't know about the rest of you, but for me, like the original concept by Justin on what based rollup is was like kind of a guiding light rather than the set in stone design and architecture. And I love the suggestions that you have there, especially the ones around execution tickets. And I think that a solution that essentially draws from the validator set, but does not necessarily have gaps between the validators, so that you don't need to wait like to find a validator that's willing to be a preconfirmer, but rather have a steady queue of preconfirmers, is going to be a possible solution to what you are flagging there. Yeah, would love to see something like this. I'm personally also working on something similar that I would love to share probably sometime over the next weeks.
Thanks, George. Looking forward to your write-up. Noah.
About conditional finality. So let's say that I'm trading on Uniswap V2. I have a transaction. I put in a trade. I'm swapping E3 USDC on. Let's say I'm on roll-up 1, and then let's say Justin's trading right after me, and I say that I'm doing conditional finality. So I'm gonna only wait for a stronger finality guarantee. Is Justin trading off my state or a different state? Because that seems a little bit odd. It's kind of the conditional finality for the user state.
Yeah, so this is a really good question. So yeah, so there is some interdependencies there. So if you're using like some sort of a shared contract like Uniswap, if so you actually could condition it off of different finality. So if Justin conditions his transaction off of one block and you condition your transaction afterwards off of a deeper Ethereum block, then it's possible that your transaction will be included and Justin's will not, even though yours came later. But that might not be maybe what users want. And so this is an open design question. How we would do this is that we might want to say, hey, if you're interacting with something that interacts with the L1, then, any future transaction of that is going to have to be conditioned on like the latest Ethereum block that is conditioned on. Because obviously a lot of users, like the user wants to, as a user, you probably don't want your transaction to be included if Justin isn't. You want it to be included if Justin's is. So yeah, this is an open design problem about how we kind of represent this like intent of what users are going to want to be conditioned on, but it's a good question.
Thanks for the clarity.
Sorry, Rohan, we have to move to the next topic, but we will have a post-call discussion to discuss further. The next presenter is Cooper from Aztec, talking about layer 1 builder censorship.
Hey everyone, hopefully you can see this okay. Cool. We're talking about the Ethereum shared sequencer and Preconfirmations. Obviously I work at Aztec Labs. L1 builders are frequently censoring people. I don't need to explain that to everyone on this call. Shout out to Tony for his lovely websites and diagrams. To give you some context, I'm thinking specifically through the lens of Aztec's designs and how we would pivot to potentially use the Ethereum shared sequencer. So option 1, just the TLDR, is like you have a proposal, randomly elected sequencer publishes a transaction ordering to L1. You'd have a separate phase where that proposer chooses a specific proving address. They put up a bond. At some later point, that prover submits those proofs to L1. Super high level, hand wavy, click the link and I'll share it in the channel afterwards if you want to read more. And so mapping these kind of phase analogs to using the Ethereum shared sequencer, right? Phase 1, super obvious. Aztec's proposer becomes, generally the Ethereum proposer. Seems likely that we would need some customized builders or dedicated actors for the Aztecs ecosystem to kind of bootstrap it, resulting in this kind of like gap period before what I think is called the super builders come in. So at some point, Ethereum shared sequencer, the people using the shared sequencer need confidence that they actually have the underlying block data. So in Aztec, because we're a privacy protocol, these are client-side generated zero-knowledge proofs. You actually need most of those zero-knowledge proofs in order to know that this block is going to become valid. And so I think that this is a largely unsolved problem. Likely all zero-knowledge rollups are probably talking about this right now in one way or another as part of evaluating this design. I would say from our perspective, the Ethereum shared sequencer seems way easier to integrate into an optimistic rollup, but maybe we're wrong about that. And then phase 3, someone submits this stuff to L1. So it's like pretty similar, right, in mental models. It's not a huge divergence of what we were previously thinking. And so there's, 2 specific concerns that I think are somewhat well articulated. So you have weak censorship, which is delaying transactions from phases 1, 2, and 3 from the previous slides, or delaying blobs from 1, 2, and 3 from the previous slides. Blobs would probably be only uploaded in phase 3 or phase 2, depending on how strong DA guarantees you need to provide to whatever proving network your zero-knowledge rollup ultimately decides on. And then there's strong censorship, and that's like builders just flat out should refuse to touch Aztec transactions because it's too messy or complicated. And depending on the severity of these concerns, we might want to redesign this block production scheme in these phases to publish to L1 eventually, rather than trying to provide more real-time finality. So if we're trying to get a bunch of blobs into blocks every 3 minutes or every 7 minutes, that could have much larger censorship implications than if we're happy just getting in every 24 hours. And so we would need to potentially redesign to accommodate that. That doesn't prevent strong censorship, and we need to land a bunch of data on chain at some point. And if that doesn't happen and you're a privacy first rollup and you need to get included from the builders and they won't, I don't know what happens. Do we pivot to becoming an L1 or something like that? I actually don't know what happens in that case. And so this is just like a high level list of things that we think what it would take to use the Ethereum shared sequencer. I don't think all these are required in like an MVP or like a first iteration, but these are the things that we see as important. So like inclusion lists with blobs. Right now we have a godly 32 kilobytes per transactions due to client side proofs. We have some other options, which is like, invent a new fancy proof compression scheme, become a Validium, which is controversial, as all are aware of for various reasons. We have some more information on why this is the case. We would have to have a pretty clear understanding of builders' compliance needs and concerns. We don't have an enshrined or canonical bridge or portal. So, we do think that compliance challenges should be implemented at the actual bridge level rather than the message inboxes for our given rollup. We would need to have much better understanding of like the peer-to-peer network and other networking considerations. Like privacy rollups have a shitload of data that honestly no one else realistically has to deal with. And so that's probably why a lot of the other twos aren't really talking about it. And then, back to phase 2 from the previous slide, like we would need some mechanism for delegating proof rights. We're currently in the Fernet designs have something that we're calling prover boost, which is just an auction for the rights to prove a block. But I think all ZK rollups need kind of clarity on what the ZK integration with the Ethereum shared sequencer ultimately looks like. And they'll all take different design trade-offs, right? Aztec has different concerns than potential other L2s. And then I would say outside of the Ethereum shared sequencer, we would love and are very excited about blob and block futures on inclusion specifically. I would say from our design challenges, we care more about inclusion than actual state results. One of those seems much easier to engineer. And just knowing that, let's say Aztec can land 7 blobs within every 4 minutes is like a super nice guarantee to know, or even just to know what the relative cost of that inclusion might be in the future. So these are things that would help us gain confidence, and trying to articulate that even if we don't go with the Ethereum shared sequencer, we see value in these inclusions and these preconfirmations. If you want to help us out, contact me on Telegram or email. If you could give us a specific sense of your compliance requirements, that would be incredible. All of our research specifically on block production is public on our forum. You can advocate for the prioritization of inclusion lists. And I think every rollup is going to be saying this forever, but increase the DA limits. And yeah, so that's my take on builder censorship. Thank you all for letting me present.
Perfect. Thank you, Cooper. Any clarifying questions from the audience?
Yes. Cooper, what was it that you said about if people could clarify regarding the censorship or compliance requirements? Do you mean from the perspective of the validators?
Yes, in terms of builders
or
across the board, just getting a better sense of your compliance requirements would be super helpful.
Okay, we can chat about it like offline, but like we have a lot of insight on it.
I would love your help there, Yuri.
Cooper, it might be helpful for you to elaborate a bit on the concern. One of the concerns you highlighted about needing the proof data to be available, and how this is different from, I guess, general data availability concerns, like the unique aspects of this problem for Aztec.
Yeah, so in our case right now, if you propose a block and it has, that block is composed of client-side generated zero-knowledge proofs, at the time that you're proposing it, you don't necessarily yet know if all those proofs are valid. You haven't proven them yet. And so you're subject to potentially like proof withholding tax or invalid proof attacks, where they're putting up block proposals that contain proofs that could never be proven. And so we either have to re-architect our entire proving stack and our execution environment to support like some type of like reverting zero knowledge proofs in some way, Or we have to make sure that at the time that they're actually being committed to, there is sufficient data and sufficient confidence that they will eventually get proven. We're working on other ways where you can like kind of optimistically verify them, but the current challenge fundamentally comes from you can't include a zero knowledge proof in a block that can't get proven.
In other words, you want to make sure that something doesn't get pre-confirmed before you know that it will be able to be proven.
In our case, we don't want it to be proposed before it can get proven, or we need to redesign a way that we can basically filter those unprovable transactions out in an elegant way, before they get finalized on the chain.
I mean,
Yuri.
is it fair to say that a block cannot be finalized without a proof?
Yes.
Okay, one last question. Yuri, go ahead.
Yeah, I just want, Cooper, could you explain that last piece between you and Ben? Basically, you want to pre-conf a proof, but you don't want to commit to it yet because maybe it's wrong or it goes on forever, etc. So you kind of like want to buy the pre-conf, but the ability to back out of it if you don't want it to. Like I'm not sure I'm clear on what is it that Aztec needs in really simple terms.
I would bifurcate our interest in pre-confs from needing a proposal phase that says that this block proposal can eventually get proven, or we can filter out the proofs in that block that will not make its way into the final proof. Does that make sense? So I would think about it separately from the pre-confirmation.
Perfect. Thank you, Cooper. Again, we can discuss more after the call. Jonas is next, talking about pre-conf delegation and centralization concerns.
Can everyone hear me and see my screen?
Yep.
Okay. Awesome. So yeah, I'm going to be exploring the pre-confirmation delegator model, and specifically like these questions. Which existing party is most suited to take on the pre-conf role today? And what are kind of the risks associated with each party? First, some quick definitions to make sure we're clear. So the sequencer is an L1 proposer that is opted in to be a sequencer for a base rollup. And for the purposes of this presentation is also delegated to a pre-confer. A pre-confer is a sophisticated actor that can handle the requirements of giving pre-confirmations. And he's also given full sequencing rights by the sequencer. A liveness fault is a violated pre-conf commitment due to a misblock, which can be either the fault of the pre-confer or the L1 proposer. And a safety fault is a violated pre-conf commitment due to just a different block being proposed, and that is fully attributable to the pre-confer. So a delegation model schematically looks like this. You have a sequencer that delegates like all of the pre-confirmation rights and sequencing rights to an operator, which we call the pre-confer in this scenario. And the users interact directly with the pre-confer and not with the sequencer. Scope, so focus is going to be based on base proposer pre-confirmations, so non-L1 pre-confirmations. And the roll-up block building strategies is kind of treated as a black box, or we can just assume that the pre-confer runs a first come, first serve strategy. So in terms of candidates, like the first most obvious candidate is kind of the relay. And that is because the relay is trusted by the validators already, or by most of them. So there is kind of a small leap in terms of trust for pre-conf delegation. They're already a highly sophisticated entity, so they will be able to handle the requirements. And they have this visibility into the execution payload, and given some small changes to MEV boost, also a way to communicate constraints to builders. But there are also a couple of reasons why relays are not maybe the ideal party. So there is kind of an increased dependency on a trusted third party that the roadmap is kind of moving away from with like PBS and execution tickets, at least as it is today. It's also pretty complex because sequencers need to be restaked for liveness faults, and there needs to be some sort of like mutual slashing mechanism, or at least a way to determine in case of a liveness fault who was actually at fault. And then I would also say, like, in terms of centralization pressures, if there is a relay that's like a first mover and that garners delegations from like most of the sequencers, there's effectively like only one or two preconfers that are sequencing L2 blocks, which becomes like a single point of failure. And then finally, we do have a dependency on restaking, again, because of the liveness faults and because sequencers need to be able to be held accountable. But aside from that, I think that for solo stakers, the relay as a preconfer is actually a good idea. But can we do better for like the largest part of our economic security, namely node operators and staking pools? And additionally, can we move faster to a proof of concept without needing like a restaking and other dependencies? So given these points, I think that node operators are also in a very good position to run preconfers, mainly because the sequencer and the preconfer in this case is the same entity. So there is no delegation of trust, which then leads to more capital efficiency. Like there's no additional stake that needs to be put up from the sequencer for liveness faults, because safety and liveness faults can both result in preconfer slashing. It's also less complex, so we don't need this mutual slashing and restaking in case of a liveness fault, and there is no revenue sharing. The sequencer doesn't need to share revenue with a third-party preconfer because it's all internal. And also, it's more. I would argue that it's more decentralized. So there are more node operators at this point than there are relays. So there will be this kind of forced rotation between preconfers based on who the next sequencer is. So I think like implementation-wise, it could resemble something like Solana's Turbine. And so, yeah, this is something that I wanted to bring up. Like, I think that in the short term, I think node operators are probably a good way to get to a proof of concept, and also might reduce some of the centralized pressures of having like one or two relays become the de facto preconf provider, if that makes sense. So yeah, that was it. And we're chainbound. We're looking into building high performance preconf infra. If you're interested, please reach out.
Perfect, thank you. Yuki, you have your hand up.
I have a quick question. So you mentioned on the first one that relay could be a potential preconfers, but and then you also mentioned that the restaking could be one way to bring accountability to the liveness fault situation, which is when there could be some sort of a missed thoughts. But don't you also think that try to bring accountability in the relays as a preconfers in the case that when we don't know exactly the cause of the missed thoughts could be a bit I guess like mistakenly slashing the relays in that case? Like, for example, if the missed thoughts were potentially due to just like the proposers just simply not proposing the block or something, like just they gave up on calling the get payload, for example, then there was simply no block. That would not be a problem of relays in that case.
No, exactly, and that's why the L1 proposer or the sequencer in this scenario also needs to be staked, and there needs to be some mechanism of determining like who's at fault here. Is it the relay? Is it the preconfer? Or is it the L1 proposer that just didn't propose a block?
So you're saying like both the relays and the proposer would be like sort of like a double stake, or in the case like it's like both restate? Is that what you're saying?
Well, the relay as the preconfer would put up like a large amount of stake, enough to become a preconfer, and then the sequencer or the L1 proposer could kind of restake a part of their stake to take on penalties if they fail to propose a block.
Thanks.
So they would both need to be staked somehow. Yeah.
Ben.
Yeah, so what do you mean though when you say they need to stake enough to become a preconfer, but what's the mechanism for electing them? What's the mechanism through which they become elected? You can have many parties that are staking, and then you have to choose one to become a preconfer. So I just didn't understand the proposal.
Yeah, I see. I think so. A preconfer could like stake in some sort of contract registry. And then the sequencers that want to delegate to that preconfer, they would somehow signify by signing a message that they want to be delegated to that specific preconfer. And then like as a client, as a user, you would somehow read the on-chain registry, see like which is the next sequencer in line and who is he delegated to, and then kind of requests or send your preconf requests to that specific preconfer.
I see. So you're saying to allow the L1 proposer to just delegate preconfer rights to someone, and just there's an additional requirement that the only people they can delegate to are people who have staked in some contract.
Exactly. Yeah.
And the last slide you had, could you go to the last slide? So I didn't understand the point on this slide. So can you explain? This is can you re-explain it? Who are the node operators you're talking about here, and what do you mean by no revenue sharing? Also,
right. Yeah. So like I probably in a case of like a delegated preconfer, if the relationship between the sequencer and the preconfer is kind of untrusted, the preconfer is taking on these additional duties it's taking on additional duties that it performs on behalf of the sequencer, right? So it needs to be paid somehow. But if the validator set or the node operator, and with node operator I mean like Chorus One and these like the bigger node operators, if they can internalize all of that, then they don't need to share revenue with someone outside of their organization, because they are technically competent enough to run their own preconfer, if that makes sense.
So the node operators are also the L1 proposers, or?
Yes.
Yes.
So this is saying,
Yeah.
let's let the L1 proposers be preconfers.
Yes, given that they can put up enough stake and choose like one delegator to accept all of the preconfs.
Perfect. Thank you, Jonas. Next up, we have Ben, who will talk about MEV misalignment between the rollups and the proposers.
Thank you, Justin. Yeah, I don't have slides, but it's very, very short, and we can leave most of it for discussion. So in the vanilla design of based sequencing, we just give the L1 proposer the right to propose the next blocks for all the rollups that are involved. And what this means is that it gives this L1 proposer entire ability to capture any form of sequencing revenue that's not being charged within the rollups itself. So everything beyond the gas that's being charged within the rollup execution environments themselves, and in particular that includes all forms of MEV, so all arbitrage opportunities, and you can even think of preconfirmations and the tips that are being paid for preconfirmations as also a form of MEV, and all of this can be captured by the L1 proposer. And importantly, the protocol is not even aware of how much is being captured, right? Because the L1 proposers are not selected in any smart way. They're not selected through execution tickets. They're just selected randomly. And so this creates an incentive misalignment problem for rollups, because great, you're joining an Ethereum shared sequencer, but on the other hand, you're, as opposed to running your own sequencer, now potentially giving up on a large portion of your revenue. And so the question is, how could this be designed in a way that does give, shared proposing rights to the L1 proposer, so that we can increase the utility of the system for everyone, but that does not get all the value to flow to this shared proposer. There's a way for the protocol to capture this value and also redistribute it potentially to rollups. So I wanted to spend mostly just highlighting the concern. I've talked about before in these meetings how there is at least one alternative design, the one that we've been describing at Espresso, which is to run, even if we can't make these changes to the L1 today, you can still run an auction or a lottery mechanism, basically execution tickets to select these pre-confers. So not to make the pre-confers just these parties that can be delegated to, but actually to elect them through a smart mechanism. And then later give the L1 proposer the ability to decide to buy those proposing rights from the pre-confers. So by default, the pre-confers actually have the right to produce the next blocks. And instead of saying that the right goes to the L1 proposer and then it delegates, rather the L1 proposer always has a right of first refusal. It can always buy the proposing rights from the auction selected pre-confers. And now we know inside the protocol how much the revenue is and where it's coming from, and we can by designing the auction appropriately also figure out how to redistribute the marginal contribution of each rollup to the overall revenue. I think Uri has a question.
As always. So what
When are
you're
you
saying
gonna have questions?
So basically you're saying that, listen, if we just give the rights to do that, then all the MEV leaks to the L1, just like it just goes there, and therefore none of the value actually stays with the rollups. And like, how could we find a better solution for that? And what you're saying is, if the shared sequencer, which is not the L1 proposer, like some mechanism kind of in between, those have the right, and the shared sequencer and the L1 proposers buy, whether execution tickets, whether some other mechanism, they buy this right to do it, then the value won't leak to the L1 proposers, and instead it would go to that mechanism, and then you make like a leap, and from there it could go back and be redistributed, etc. And I want to put a question mark on that leak. Like, it makes sense. Yeah, don't let it leak all the way. You stop it here. Okay, now it's at the shared sequencer, so all the MEV is at the shared sequencer layer. How is it easier to push it back to the rollups from them compared to getting it from the L1 proposers? Or like, do you have something concrete in mind?
Oh, definitely. It's concreted. Yeah, it's also explained in the HackMD post. I'll drop a link to again. But it's not that this is an implementation of the mechanism through which pre-confers are elected. So the pre-confers are elected through an auction rather than just being assigned to the L1 proposers. So the auction is run in a way where rollups are effectively selling or auctioning off their block proposal rights to pre-confers. And the results
it's kind of like selling order flow, really, right? Like from that level, it's not like
very similar to selling order flow. And in fact, a rollup could set a reserve price that says the shared proposer is only going to be able to buy the right to propose my next block if it pays over this price. Otherwise, I propose my own block. So this also allows for, it doesn't force a situation where there's always one proposer for all rollups. We could have situations where there are in certain slots, there are multiple proposers who sort of partition the rollup space. As long as the shared proposer is creating an economic surplus, then, and if the most economically efficient allocation is to have one, shared pre-confer that's going to propose the next block for everyone, then the auction will find this solution. But by basically allowing rollups to sell or auction off their block space in this mechanism, you allow them to capture value.
Interesting.
Kartik, sorry, we're out of time. Thanks, Ben, for the presentation. Next up, we have Ye from Scroll talking about scaling bottlenecks with shared sequences.
Okay, sure. Thanks. Sorry, also because the writers are very late, so I also don't have time to prepare slides. So really sorry for that. But I want to bring a different view for like this shared sequencer, because people talk about pre-confirmation, economic guarantee a lot. I want to talk from a very, very different view around like performance, because the way I think about layer 2 and layer 1, the relationship between like two layers is that layer 1 actually solves this kind of decentralization, like, consensus, all those problems. So all the things that, because I think about layer 2 or any blockchain, like as a database, like where, and also processor. So basically like this processor receive transaction and can read and write into this kind of database. And then like because you want decentralized, so you need consensus among those kind of database. So you have layer 1. But it's not efficient enough. So the way I look at about layer 2 is that, okay, so right now let's forget about decentralization, just focus on performance first. So it's like basically like a layer 2 is building a high performance, like, DB system with a processor and processing your transaction maybe in a centralized way. And then it can read and write into this database and process transaction really fast. And then all the security decentralization is guaranteed by posting a proof to layer 1. And now, like if you want to have shared sequencer, especially if you have this kind of atomic compatibility between two kind of different rollups, so what you are assuming is that it's a distributed database system where you have two different databases, you have two processors, and then like normally like they only read and write into their own state. And now you are basically allowing this kind of like atomicity between like two different like such system, which is like this processor sometimes can write to the database of the other rollup, and which actually cause a big problem for like, if you look at that from a view of just a distributed system or high performance distributed data DB system, because there are two like, different like guarantees for consistency between like because sometimes like you will have read and write conflict because the other rollup will like, when they are maintaining their own state, their own database, they can write to some state, and the other rollup can sometimes also like write to the same state. So you kind of need some locking mechanism. So if you have to take some term from the field of distributed system, there is like two ways. One is a weak consistency, one is a strong consistency guarantee across multiple different replicas. So, and in blockchain, we definitely need strong consistency. The requirement for strong consistency is that all the kind of updates must be immediately propagated to all the copies. So it has a very, very strong requirement for like, some global synchronization mechanism. And it's like in the literature of our distributed system is like, it's very unfortunate that, such mechanisms are very, very hard or even like impossible to implement in a very, very scalable way, because it's just fundamentally like very bad to enable such kind of like read and write into like, different system, and especially with the possibility of revert. So it will massively, so imagine like, you are building one single system. You only allow that to happen within your own system. You can make that super performant, like Solana or like some really, really high performance chain. But now once you enable the possibility for like, cross read and write and enable this possibility for having conflicts, then like the performance of each system will be massively decreased, especially if that because that need to be considered into part of your system design. So that would cause like the performance of both sides become seriously like massively influenced. So that's a problem. Like when I'm talking about this problem with Justin, like, one immediate solution, which from Justin, and also like we have Muhammad, like researcher Muhammad working on this, is that, okay, so can you have now, like, if you have this kind of enable cross-chain transaction and read and write into your own state, that's a problem. Now, can you kind of like, maybe like, if one is operating the both rollup node, can you have like design some mechanism where like every time block there is a like super like a different like block that only contain like cross-chain transaction, super transaction, and as far as it's economically viable because some people want to pay more, and then you can make this kind of only happen within a certain period of time, so that in other time you only need to handle like transaction within your own system, so you can still design that in a very, very high performant way. But this design also requires the same block time, also has a very, very centralized assumption that one entity have to operate on both sides. And also it's actually a trade-off between liveness and economics, because imagine like, you have like one half of your time just producing like, processing such block. So which means like one rollup's liveness can also influence the other rollup liveness, because one rollup, when sending a cross-chain transaction, can lock the state in the other rollup, which will influence at least like, your performance will be like half decreased. So there is a like trade-off between like how much, economically you want to kind of like make this happen versus like, in reality how much it influences the performance. And so like eventually, like we don't want to end the game where, you know, some people can send an atomic transaction to lock the state on both sides so basically influence the liveness on both sides with a very, very cheap, just one transaction, and which will like make this kind of actually less scalable. And especially like, you know, we are thinking about like a very, very scalable future where, you know, the Ethereum and plus its oil layer 2 are really processing like 10 million transactions per second. We really need to think from like not just economics, not just like, you know, this kind of like blockchain perspective, but actually from a way for how we build a like performant enough system to kind of handle this. Like imagine like if you allow this compatibility happen between like 100 different chains, each chain maybe maximum throughput might be like 1,000. And then you need like way more such kind of system to kind of like talk with each other like within like some block time, which will massively influence, even like you add up all those kind of 100 chains, what the performance will look like, what the user experience will look like, and is this kind of really designed for massive adoption? So it's a very tricky question. So yeah, those are like some of, and also like, you know, especially because this can only happen with ZK proof and like real-time ZK proof. So there will be also some dependencies when you have this atomic compatibility for like, you know, because basically like, you know, imagine like I want to swap to on the other rollup, I need to send a transaction initiate on one chain, swap on the other chain, and send it back to my own chain. And then the ZK proof also requires state that is like, you know, dependent like for each transaction. So you need like real-time proving for each transaction. It's not just block level if you want to ignore all the optimistic assumptions. So there will be a lot of like dependency issues on actually implementing such a system. But again, like, you know, we are still like working on research on this direction, but I just want to bring a totally different view on like not just economics, but actually from massive adoption, how you build a really, really high performance system and what the future will really look like if you want the whole blockchain system need to handle like 10 million transactions per second. And is that like several like relatively high performance systems, and you really limit what the interoperability look like, maybe just async compatibility, which is more practical, or you want to enable this, which will influence the design for each rollup. But yeah, those are some of my concerns, just bring a different view on like, you know, how we are thinking about that. But we are also working on research to kind of help, you know, how we can solve this problem. I think Mohammed might have some write-up. But yeah, those are some of the concerns, and yeah.
Perfect, thank you, Ye. I guess Ye's talk was the first talk that was not specific to base sequencing, but applies to any shared sequencer. Do you have any clarifying questions from the audience? Ben.
I feel like I'm speaking a lot, so if somebody else has a question, you should go first. Okay, so thanks for the presentation, Yi. So I guess two related questions. One, you sort of presented as we should either decide to like limit interoperability for everyone and have better performance or not. But couldn't you imagine that there would be a design space for rollups, and some rollups would choose to interoperate at the cost maybe of throughput, and others maybe they're only servicing some like very high throughput games that don't need interoperability, and then they just choose not to.
Yeah. That's a good question. So just clarify. So I think they are definitely like design space, and to allow this happen, if some rollup opt into such system and allow economically, like they can interoperate with each other. Because if you really think about like long-term end game for rollup, like what, you know, like how many rollup will be there, like there might be very general purpose, and why people are using that is because they are general purpose, they have enough liquidity, and then they can process enough transaction. So I guess most of the well adopted like rollup in a very, very longer term will be high performant enough so that they actually need more like a synchronous compatibility to that influence their performance less, influence their liveness less, and then like there will be maybe some like smaller rollups, and then they can kind of allow this to happen, but with totally different assumptions. So I think that's totally fine. Like, you know, it's totally possible to have some rollups like designing that. But if you really think about long term, like, you know, what they kind of 10 million transaction per second, like the whole system will look like, how many general purpose will look like, what's the requirement for each rollup, and should we allow this to happen? So it's more from like a very, very long-term end game for like large general purpose rollup.
But also it seems to be it's a decision that rollups can make to allow cross-chain message processing even if they are part of the Ethereum shared sequencer or not. Like they could, in other words, some pre-confirmations don't have to do with cross-chain messaging. They just have to do with making promises over atomic guarantees. I want my transaction to execute on 2 different rollups. I don't want to actually pass messages that something confirm. Do you see, especially coming from a ZK rollup, do you see, like you talk about the these concurrent systems as and parallel processing as being very important for efficiency of processing tens of millions of transactions, but what to what degree is this like concurrency really getting around the bottlenecks, especially for I guess ZK rollups, where you're doing so much computation. I mean, so much computation to produce a proof relative to this database processing, that I'm wondering how you see when we have tens of millions of transactions and the ability to produce proofs for all of them, that the interdependencies that will be caused by cross dependencies between these databases will create a bottleneck.
Yeah, that's a great question. So because like as far like it's definitely like for prover you require way more like computation, but it's very easy to kind of also outsource to like another like decentralized prover marketplace, and then making that highly parallel and then finalize later using optimistic, like firstly you commit data and then like you later handle this. But this is will actually definitely become like state growth and all those stuff, how you process your transactions, those things will definitely become a bottleneck when you grow really, like let's say like go over like 10,000 transactions per second or something like that. So it's definitely become bottleneck, like at some point where we reach the level of massive adoption, because everyone talk about like welcome 1 billion people into ecosystem, into Ethereum, but if you really think about like 1 billion people, everyone send 1 transaction per day, it's already require over like 10,000 like throughput just like for payment like only. So it's like really like if you imagine like blockchain is really getting massive adoption instead of just like playing like a toy where you have like 10 or like 100, that will become like a very like
maybe just to clarify, I guess if 99% of your work is in the proof, then it seems like proving is what needs to be distributed. And if 1% of your work is in constructing the state changes that need to be proved, then it doesn't seem necessarily hard to construct. If there's a single proposer who's proposing for multiple multiple rollups, it could calculate for each of these rollups what the state changes. That's 1% of the work, and then 99% of the work needs to be distributed. I guess that was the point.
I totally understand that. But even that, like basically the problem, like even you allow like very complicated machine to run that, like allowing this kind of synchronous compatibility in a distributed system is just it's a bad design from like how you design high performance system. And that's basically a conclusion from the literature of another like space, and which like we are working on some benchmark and looking to like some practical like evidence, but those are like we can discuss offline.
Perfect, thank you. Next up we have Alex from ZK Sync, but I'm not sure he's on the call. Alex, are you here?
I think Alex is on a flight.
Oh, okay. That explains. Great. So we have time for the last talk as well. Alex Watts on pre-confirmation-based market manipulation.
Hey, everybody. My name is Alex. I am the founder of Fastlane Labs. We're an MEV company focused on validator-aligned MEV on Polygon and app-aligned MEV on pretty much everywhere else. I wanted to go over one of the potential attack vectors. And I find this attack vector to be particularly nefarious because it's not one of the most intuitive ones. The way the attack vector comes about is when we start looking at pre-confirmations as including information on the result of the execution of a transaction. And so if we look at splitting the, hold on, I think my Zoom is disrupting me a little bit. So if we look at splitting the value of a pre-confirmation into 2 components, you're looking at the inclusion being one and the information being another. There is a lot of value in that second component. Efficient users, power users, think stat-arb teams, etc. What they will try to do if they want to be as efficient as possible is cram as much information requests into the return data of their pre-confirmation, such that when they are getting back this, low latency, like very high speed pre-confirmation result, they are going to have a lot of visibility on the new state net of a series of other pre-confirmations that would have been happening before, which would also be very latency sensitive. So what this does is it opens the door for a few different attack vectors. The main one that I'm going to focus on today is the fact that people's actions, especially for bots and other automated traders, are often a result of other prior actions that happened before. For example, if a bot wanted to purchase 1,000 JD coins on an AMM, then they may or may not then sell 1,000 JD coins on a centralized exchange based on the results of that pre-confirmation. If an Oracle updated successfully, then because they know that the Oracle updated successfully, then they won't do another update. If a swap reverted based on the pre-confirmation, then they might initiate another swap on a different AMM. If a balance increased, if a balance threshold is met, then maybe a off-chain auction OFA mechanism might match an intent to this user whose balance increased, because now they have enough of a balance to actually fulfill an intent. And so what I want to focus on is the fact that pre-confirmers can actually attack users without violating any sort of inclusion or sequencing guarantees, solely based off of giving them incorrect information about what happened to their transaction. As an example, let's take a user who wants to do a swap. Let's say this is a StatR team of some kind. So they send in a transaction to do an arbitrage swap, and as part of the return data, they want to get the rates of the pools after the swap. What was the price impact? What was the success? What's the current rate now? And maybe they want to do another swap afterwards. And so the pre-confirmation or the pre-confirmer could take this swap, execute it exactly when they said they would, like sequence it correctly, but then lie about the return data. They could tell the bot, hey, your swap reverted, sorry, but by the way, these are the current rates based on the state requests that you put into your transaction, knowing that the bot would then see the current rates and think, oh my gosh, there's an arbitrage opportunity still, I should submit another transaction. But in fact, the bot's transaction did go through, so now they're being artificially tricked into doing a second transaction, a second swap in the exact same pool that the pre-confirmer is telling the bot is a good pool to swap in, which the pre-confirmer now is able to sandwich. It essentially knows how the bot will react because it's a bot, it's predictable, that's how bots work. And so the pre-confirmer can actually, like, very high confidence, sandwich the bot based just off of the return data that it gives to the bot. And that is a very, very tricky thing because it can do this without violating any sequencing guarantees whatsoever. It can stick to the entirety of the sequence, no problem. So there's a solution. You could have the pre-confirmer or pre-conferrer sign the return data, but then you start running into some issues with latency races, such as how do you know that the return data is fake? One of the ways is you could actually have a P2P gossip network. You could have return data get gossiped among a set of peers. But keep in mind that this is, you have to prove a positive rather than the absence of something. And so in order to detect some sort of equivocation or fake return data, even if the pre-conferrer is sending out like the real data, which they would presumably do so they don't get slashed, they can even try to trick that. They would send out real pre-confirmation data to all of the other nodes, and they could send out the fake pre-confirmation data to the user, which, by the way, in the MEV world, it's fairly straightforward to identify the IP addresses of all the major players. So I think we should assume that they can be detectable unless we're looking at the encrypted P2P layer, which I know a lot of you guys are working on, which is pretty cool. But anyway, I say all this to say that it does become a latency race, and it would be trivial for the pre-conferrer to delay propagation of the real pre-confirmation result until after it knows that the target, the victim, sees the fake data and has time to respond to it with another real transaction. There's a lot of different potential attacks. It's not just the sandwich. Some of them are quite nefarious. And importantly, if the preconfirmer knows that it's going to be slashed, it can just stack these up. The slower the nodes in this P2P gossip network, the more vulnerable they're going to be. And the majority of the solutions to this problem have a significant impact on scalability or throughput, as Ben and Ellie have been talking about a lot. So I'm going to skip that part of the slide deck because you guys hit pretty much every point that I was looking at. The other like huge issue though is that if you did want to have a user like validate it in real time without having to rely on a gossip network, and you do have these preconfirmers signing off on the hash of the return data as well as the hash of the previous hash's return data, then you would need each user to have full visibility on all of the transactions that came before it. That also has some scalability issues. That has huge issues and impacts for cross-chain and interop. And it kind of also just like really incentivizes vertical integration because it's quite difficult to price this kind of thing otherwise. The biggest issue is that you can calculate like whether or not something like this would be profitable before you even like do the attack. And so when you're running into like insurance and insurability for something like this, you generally want to make sure that you don't have like a hugely adverse selection component where, you know, the attacker would only do the thing you're trying to insure if they know that they are profiting more than the, you know, insurance would cover. So it does make pricing insurance quite difficult. Collateral dilution could also get reused excessively. But yeah, that's the general idea. I know that there are some sequencer specific mitigations that could be used. I'm super excited to learn more about those, but I think in general, this is something that we should definitely keep an eye on as we dive deeper into this. The validity of not just the sequencing, but also the result.
Perfect. Thank you, Alex. I guess Alex's talk was the first talk that was even more specific. I guess, well, I should say even less specific because it applies to all sequences with these types of preconfirmations, not just base sequences or shared sequences. We have a couple hands up and then we'll close the call. Kartik and then Noah.
Yeah, thanks, Dogard, for presenting this. I didn't really think about this as an attack vector, but it definitely is. That being said, a few things to push back on. One, given your construction, like your initial solution of just having them sign and then imposing slashability conditions on if they sent the wrong data, which is easily traceable after the fact. I don't think that the premise of them only taking these opportunities when it is profitable necessarily holds, because the actual precon for themselves is kind of doing like a stat arb in and of itself, right? Where they're sending incorrect data, but they don't have confirmation that the actual MEV bot is going to act on this data in a way that's going to be profitable for them. So I think the dominant strategy for the bot would be, okay, let's opt into both the precon for signing whatever the post date route is, or like whatever transaction data I want after my swap executes, and then also wait to hear from X other nodes who have gotten this gossip to them. If there's any disagreement, then I can slash him. If there's no disagreement, then I can continue with my swap accordingly. And then that's just negative EV for the actual precon for in this setup.
So I would push back on the first part. I do think it would be very high conviction for the attacker to know ahead of time what the profit would be. The way that you can calculate volume for stat arb like this is looking at the liquidity of the pool as well as the spread, like, you know, the rate delta between, you know, Binance and Uniswap. And so like there's not that much drawing outside the lines of all the major market makers, if we're being honest. And so
well, I don't think it's on the actual pricing of it. I think it's the uncertainties coming from, is this player going to execute how I think he's going to, if he's running a naive bot that like immediately sees this and trusts it, or is he going to wait a little bit, get confirmation from another node that, okay, this is actually correct. If it's not correct, then he's going to slash. If it is correct, then he'll execute.
But if we're looking at like a first come, first serve thing, then anyone who waits will never win.
Well, I think this will just be the dominant strategy in that, you know, thing. And then you're only waiting like one network hop, which is minimal latency, maybe like 10 milliseconds.
Right, but like there's going to be someone that doesn't want to wait and actually wants to get the money, and like you wouldn't be able to know ahead of time. So
Sure. I guess that'll just get priced in.
maybe.
Alex, thank you so much for your presentation. Noah, if that's okay, we'll move your question to the post-call discussion. Thanks, everyone. We're closing the call here, and chat soon.